Why, hello there. Welcome to Homework Keys. I'm going to do these three homework keys for starting with rotational kinematics, then torque, and then moment of inertia. And um, remember, too, for this stuff, that the AP exam is going to be open book, open note. And so there are some shortcuts that you can take for some of these things that will make them much easier, especially for moment of inertia stuff. So to start off, we have our disk starting from rest and accelerating uniformly, uh, changing its angular speed from 0.25 revolutions per second, from 0 to 0.25 revolutions per second in 27 seconds. And it's asking, what is that angular acceleration? So given the question that it's asking, angular acceleration, that's going to be equal to the change in angular velocity over time. Remember that this is analogous to our translational or linear A equals delta V over T. Rotational acceleration alpha equals change in rotational velocity delta omega over time, t. So in order to answer this, I'm given time, 27 seconds, but I'm not given delta omega. What I'm given is the change in revolutions per second. Remember that omega needs to be an angle per second. So this should be in units of radians per second. So in order to convert my 0.25 revolutions per second to radians per second, I'm going to multiply that by 2 pi radians per revolution. So my revolutions will cancel, and I'm left with 0.5 pi radians per second. That would be my delta omega. So then it's just a matter of plugging that in. So you should have that conversion be your starting point, and then substituting that back in to your equation for alpha. And that would be it. So don't forget about the unit conversion there to radians per second. And then here we have, would doubling angular acceleration double the final angular speed? And this is a great type of exam question for this year because it is a conceptual question that you have to know the math in order to answer, but you don't have to actually do calculations or show math in order to do it. So what I would say is, given the equation for final angular velocity, that would be omega equals omega naught plus alpha t. Given this relationship, omega is directly proportional to alpha. That looks really weird. But that is, omega is directly proportional to alpha, so doubling alpha would double omega, given the same starting omega and the same time interval. So there you go. Moving on, during a certain time interval, the angular position, so angular position, that would be theta, of a swinging door is described by theta equals some function. Ooh, function. Sounds like we're going to be doing calculus on this question, where theta is in radians and t is in seconds. So this is a function in terms of time. Determine the angular position, angular speed, angular acceleration of the door at the following times. So for angular position, here, this is just substitution, right? We'd say substitute t and solve for theta. Easy. Everybody's going to have a different formula here, so I'm not going to actually bother solving it out. But yeah, you just substitute in time, and substituting in time would give you the theta there. Now, when we get to omega, angular velocity, and alpha, angular acceleration, we'd have to um, manipulate this function for theta such that it then describes omega. So we would say omega is the derivative of theta with respect to time. So we would take the derivative of this relationship, then substitute t and solve for omega. And then lastly, for alpha, we would say alpha is the derivative of omega with respect to time. This is the same types of relationships from our translational or linear kinematics, right? That velocity is the derivative of position and acceleration is the derivative of velocity. Same stuff, just applying it to the angular context here. Then substitute and solve. And the same thing is true for the second part here, ditto. You just substitute in a different time for each of these values. So again, is this like we're doing new stuff here? Technically, it's new, but it's really just reapplying the things that we've already learned in a novel context. And that's what this whole thing is about for this class, right? So much of this class is about, building a foundation and then being able to apply that foundation in new ways and meaningful ways. Moving on to question number 3, we have a centrifuge. Look at this crossover. Physics crossing over with biology because we're in a forensics laboratory and we're given an angular speed of 3,800 revolutions per minute. Remember, we need to convert this to radians per second. So that would be, in this case, 3,800 rev per min times 2 pi radians per revolution times 60 seconds, divided by, my bad, times 1 minute over 60 seconds. And then our revolutions would cancel, our minutes would cancel, and I'd be left with radians per second. Okay, then we're switched off, and it gives us a number of rotations before coming to rest. Okay, so what that's telling me, it's giving me the original angular speed. So omega naught is given here. These are our givens. Omega naught. And that omega naught is given here. This is my omega naught. It also gives me this number of rotations before coming to rest. So coming to rest would suggest that the final velocity, angular velocity, is 0. That's also given. So we'll highlight that in a different color. And it gives me this number of rotations before coming to rest. This is a number of revolutions, which is telling me the angle that it rotates through. Except that it's not giving me the angle in terms of radians, it's giving me the angle in terms of full circles. So we need to, again, convert to radians. That would be, in this case, 48 revolutions times 2 pi radians per revolution. And that would give me the conversion here. But this is also telling me what my delta theta is in this case. My change in angle as I'm accelerating. And it's asking me for what is alpha? What is the angular acceleration? So here I'm given starting velocity, ending velocity, and displacement effectively, right? This is like being given delta x, v naught, and v, and asked for acceleration. But in the angular context, I'm given these in angular constructs. So if this were a linear problem, I would most likely use v squared equals v naught squared plus 2a delta x. In the angular context, it's the same equation, just applying it to the rotational construct. So that'd be omega squared equals omega naught squared plus 2 times alpha times delta theta. And then solving for alpha. So alpha would equal omega squared minus omega naught squared divided by 2 delta theta, right? And again, I'm given these values, so then it's just a matter of substituting and solving. So then this last one, the actual values kind of do matter for this problem because we're looking at sort of like, why is it impossible? So uh, the values themselves are what make it possible or impossible. So I will answer this in terms of these values, but everybody's values will turn out to be impossible as well. So starting from rest, that's a given value, right? Starting from rest is telling me that my omega naught is 0. My initial rotational velocity is 0. And then we rotate around a fixed axis through an angle of 75 radians. Angle of 75 radians, that is telling me the change in angle, or the rotational displacement, or angular displacement. So that's another given. And we're given time in this problem as well. So we're told that time interval of 15 seconds. So time is given. We are lastly told that the final angular speed is 5 radians per second. So that's my last value that I'm giving here. What color can I use here? Here we go. So my time is 15 seconds. My delta theta is 75 radians. And so basically, it's saying, why would this situation be impossible? And so it's implying that there's a mathematical fallacy here, right? So our goal here is to demonstrate the mathematical fallacy. And the easiest way to do that, given that the acceleration is constant, would be to compare the easiest values to solve for. In this case, I would maybe look at what I'm given, an initial velocity, a final velocity, a time, and an angle. Well, I know that, like in linear world, average velocity is delta x over t, and average velocity is v naught plus v over 2. And this is true with constant acceleration. Well, in the angular world, then, the same things would be true. Average omega would be delta theta over t, and average omega would be omega naught plus omega divided by 2. And again, this would be with constant alpha, with constant rotational acceleration. So that becomes really easy math to do, right? This is pretty basic stuff. So I would say 75 divided by 15. Okay, so average omega is 75 over 15. That would be, what, 5 radians per second. Looking at it this other way, omega average would be omega plus omega naught divided by 2. Well, that would be 0 plus 5 divided by 2, which, oh my gosh, that's 2.5 radians per second. And these are not equivalent. Whoops. So these are not equivalent. Therefore, impossible. Right? If this was in fact constant acceleration, then these two values would be equal to each other. Because they're different, then this situation cannot be constant acceleration. Either that or the numbers themselves are whack. So that's the end of our first little key here for our rotational kinematic stuff. And I hope that you had a good time. I certainly know I did.